Power resiliency and redundancy are critical for data centers, where even brief power interruptions can lead to significant downtime and data loss. Resiliency involves installing extra generation technologies so that equipment can still continue to operate when utilities experience outages. Redundancy deals with having internal resiliency against technological outages, so that if something breaks or a power failure occurs, the electrical demand can still be met and equipment can still continue to operate. In this video, I'll show you how redundancy modeling in Xendee is different from traditional redundancy assumptions, and how modeling in Xendee can lead to a more cost-effective, flexible, and resilient energy system that meets strict uptime requirements without unnecessary oversizing. First, we need to understand how redundancy modeling in Xendee works. Traditional redundancy follows the N plus X strategy, where N is the original number of equipment or capacity, and X is the number of backups. In this example, we specifically use an N plus 1 strategy, but with additional considerations for the smart dispatch of the technologies. This can mitigate capacity oversizing, and cheaper solutions may be possible. Here we have our data center with some solar PV and battery storage that will be installed on site. Let's pretend we have one singular 10 megawatt backup generator that's only meant to be used during outages. In the standard N plus 1 redundancy planning, a backup generator of the same type and capacity would be added regardless of how the mix of technologies is being operated. In our example, N equals 1, so we would end up with two 10 megawatt generators. However, this approach can lead to overinvestment and underutilized assets. In Xendee, redundancy is modeled as an integrated solution of both system design and operation. Instead of statistically adding backups, Xendee uses smart scheduling and co-optimization to ensure that, at any given time, a technology failure can be made up for by any reserve capacity from generators or battery storage. This means that technologies chosen to provide redundancy can also contribute to day-to-day system operation. Let's look at an example of how this works in Xendee. In our model, we have inserted our 10 megawatt backup generator. We know that we want at least one unit to serve as a main backup generator, but we're open to more because we have redundancy requirements. So we set the decision to forced plus more. However, let's see if we can meet the redundancy requirements with smaller generators. Since our site also has battery storage available, we may not need another 10 megawatt generator to meet redundancy requirements. Let's add a second generator model that's only rated at 2 megawatts. We set it to consider to let Xendee tell us how much we need and designate it as a backup-only generator. In the outage tab, we also set a one-day utility outage scenario. During the utility outage day, the 10 megawatt generator can be used to meet the electric demand. But remember, we're implementing redundancy for this specific 10 megawatt generator. Here in the optimized window, we select reduce cost as our objective. We also have to enable redundancy. Here we have to define two parameters. The redundancy level defines how much electric redundancy must be achieved in the solution. I set the level as 1, so that means at any given moment, including the outage, the reserve capacity is 100% of whatever the biggest electric provider is. Out of all the technologies in our system that might fail, we plan around the worst case failure. In our case, level 1 redundancy means still being able to cover 100% of our 10 megawatt backup generator in the event that it fails. The failure duration defines a continuous duration for which redundancy must be provided. We set 24 hours here, so that means our redundancy capacity must be capable of running for 24 consecutive hours. The optimized result tells us that our data center will benefit from installing large amounts of battery storage. In addition to the mandatory 10 megawatt backup generator, 3 2 megawatt backup generators are installed as redundant capacity. Xendee tells us that the system's reserve capacity is at least 100% of each electric generation source at any given time step, and that this 100% backup capacity can be sustained for 24 hours. Let's take a look at the dispatch to see what this means. This is the dispatch for our one-day outage period. We can see that during the day, when solar is available, the solar meets most of the demand and charges the battery. However, if PV generation were impacted or reduced, the backup generators can cover the demand as well. During the non-daylight hours, the demand is met by a combination of the 10 megawatt generator, the 3 2 megawatt generators, and the battery. Remember that our redundancy level is 100%, so theoretically, if the 10 megawatt generator fails during the outage, the load can still be met by the other 2 megawatt generators and the battery. Let's also take a look at the system dispatched during normal days. For a regular peak day, we see that the solar is also used to meet the demand and charge the battery. In the non-daylight hours, the battery is used to reduce the demand of utility purchases. In this approach, our large on-site battery capacity enables us to achieve 100% electric redundancy with only installing a fraction of the backup generator size. This results in a more cost-effective and flexible system instead of the typical N+1 planning method. So there you have it. What topics in designing microgrids do you want to see next?